Okay, next up is going to be exceptions to the octet rule. Well, you guessed it. If we do some examples of certain things, what we're going to find is, as you know in chemistry, there's always going to be an exception to the rule, right? So that means that if the octet rule says 8 electrons, then there are going to be some atoms that are going to break that rule, and they'll be able to have more than 8 electrons. Well, how might that be possible? Let's take an example. Let's do an example with phosphorus, P. So phosphorus, if you did the electron configuration notation for it, it'd be 1s2, 2s2, 2p6, 3s2, 3p3. I'm going to have a table closer to me, I guess. 3p3. Okay, remember that in the third energy level, if we did the order of filling, you would see that the d orbital starts to appear, right? That is the explanation as to why we can break the octet rule, because the d orbital can actually get involved. We call this an expanded octet. Expanded meaning bigger, meaning that we have more space for electrons than we ordinarily would. So if we're going to draw a molecule of phosphorus, and let's say it's P, let's do PCl5. What we want to do is the Lewis structure. So a little bit of review on that, right? First step, number of atoms times the group number. So phosphorus in group 5, there's 1 of them. Chlorine's in group 7, so there's 35. 5 times 7. So that gives us a total of 40 electrons. Well, what are the rules? Typically, we put the least electronegative in the middle, so let's do that. We'll put P in the middle. And now we're supposed to put 5 chlorines around it, right? Ordinarily, we'd say you can't do that because that'd be 5 bonds. What does that mean? That means 5 pairs of electrons around that phosphorus, and then you'd complete the octets of the chlorine that surround. And then in the end, you're going to come up with the molecule PCl5. Okay, well, more to it then. If we do the bonding discussion, you might recall we used orbital notation for that. Chlorine, just to simplify, would have 2s2, 2p5, so they're 2s2, and then our 3p orbitals. The last one would be half filled. The phosphorus then, notice the S is filled, the P is half filled, but in fact what happens is you get what's called a hybridization of orbitals. They start to combine. In fact, you can put up to 2, let's see now, 3, 4, you can put up to 2 extra electrons in d orbitals. There's space for it. A pair of d orbitals could then become involved. So 2 of the 5 d orbitals in the orbital notation could then be involved in the phosphorus. Well, what would that look like then? Well, if we did 3s2, 3p, there's the p's. I'm going to go this way. 1, 2. So there's my 3s. There's a 3px, maybe 3py, 3pz. And then we're going to invoke a 3d orbital. Now, if we look at those, it's 5 electrons, right? And so what we could start doing is something like this. Half filling those. I guess we just need the 1 in the case of the phosphorus here, but it would have an extra one because we could do more. So you can see what we could start to happen here. 1 chlorine then occupies this orbital combination. It's hybridized. Basically, they combine, and then we have space for 4 more. So there's 1 chlorine, 2 chlorines, 3 chlorines, 4 chlorines, 5 chlorines, and the overlap of the orbitals then allows for the formation of a chemical bond. So that is, in fact, how we're going to have those 5 bonds on the central phosphorus. So phosphorus then becomes an exception to the octet rule. In fact, phosphorus would be good then with 8, according to the original octet rule, 10, or 12. Any of those combinations are going to work for the atom phosphorus. Again, an exception. How about another one? Let's say that we were going to do sulfur, and we're going to do SF, let's see now, 6, SF4. See if we can do that. So fluorine is 7 times 20, 28, so that's going to be 34. We put our S in the middle, 4 fluorines, 1, 2, 3, 4. So that's going to be, whoops, bonds first. My mistake. Good catch if you caught it. Surround those outside atoms. How many have we used? We've used 32. There are 4 bonds for the sulfur. Consequently, 4 bonds, we have 2 extra electrons, 2 leftovers. The rule says we got to put them on the central atom when we're done. So we put 2 electrons there, and now sulfur has 10. Can it do it? Yes. In the same way that phosphorus expanded its expanded octet using the d orbitals, we can do the same thing with sulfur. So sulfur then would be good again with 8, 10, and yes, because we can pull another d orbital in there, you can pull up to 2 in these hybridized orbitals, we could do 12 with sulfur as well. Okay, so again, exceptions to the octet rule. So phosphorus can do this, chlorine can do this, sulfur can do this, selenium can do it, bromine can do it, iodine can do it. Basically, you're looking at elements that are in the 3rd period or lower, and usually non-metals, so aluminums don't typically get involved in this sort of thing, but the elements here that are below. Why is that? Because, well, the 2nd period does not have a d orbital, so it cannot expand its octet to form more than 4 bonds total, or 8 electrons. But these elements down here, now we're talking about 3p, 4p, 5p, 6p. In fact, you find also that some of our noble gases can get involved. Yikes, right? How is that possible? Well, believe it or not, compounds have been made with xenon. And so it is possible for those elements to get involved. How are you going to be able to predict? Well, for our purposes, we can say in general, we're looking at 8, 10, or 12 for those atoms. Is that an exclusive list? No. Are there exceptions? Of course. But commonly, these would be the ones we see. Okay, so expanded octets. Another piece that comes out of this is something we call resonance. And resonance really refers to structures that are made by Lewis, so Lewis structures, that have multiple possible arrangements of bonds. Now, specifically, we're looking at double bonds for these, although it is possible to have different structures in and of themselves. Here's an example of another molecule, if you will, that is different from what we've seen so far. Probably. SO4 2-. This is what we call a polyatomic ion. You might remember that as sulfate. We can apply the rules for Lewis structures to this. If we apply those rules, the sulfur's in group 6. There's one of them. Oxygen's also in group 6, so that's 4 times 6, 24. Now, if you have a negative charge, you're going to add 2 electrons. There are 2 extra electrons as part of the structure. So this is going to add up to a total of 32, which is a nice multiple of 8. If we go through the structure, we're going to put the central atom as sulfur, 4 oxygens surround. All right? Those 4 oxygens surrounding then need to have their bonding pairs. Now we complete the octets of the surrounding atoms. Now the difference with this particular structure is, since it's 2 extra negative charges, we're going to put square parentheses around this, square brackets, and we're going to indicate that it's got a 2 negative charge. That's the Lewis structure, one of the forms for SO4, the sulfate polyatomic ion. All right, the question is there another option? Can I do something else with this? Well, given that sulfur is an exception to the octet rule, remember we just saw it could be 8, 10, or 12. In fact, there is another possibility. Could we in fact make a double bond on the sulfur from one of the O's? In fact, we could. So if I take this structure and this oxygen, I could move that pair of electrons in between the oxygen and the sulfur to make what's called a double bond. 2 pairs of electrons, leaving 2 lone pairs arranged thusly. And our oxygens then surrounding that central sulfur, start to look like that. And that gets a -2 charge. These are not equivalent because this one has single bonds, that one has a double bond. But I bet you can look at that structure and say, I could draw that a different way. I'm going to draw it this way. I'm going to say the S double bond with 2 lines. That just shows it's a double bond to the O here. And for convenience at this time, I'm going to drop the square parentheses, square brackets, because otherwise it'll take too much video time. Fine. So there's one example. But who says the double bond has to be there? Could it be here instead? Sure, it could. So what we do is we draw a double arrow like that. And this shows that there's a resonance form. It's the same Lewis structure, but it's a different arrangement. So then the double bond would be on the right side oxygen as opposed to the left side. Can you see another example? Can you see another way we could draw it? Well, sure, I'll bet you can say at least 2 other ways that this could be drawn. And so one of them might be this, double bond to the O on the left side, as opposed to the right or the top. And you can see that there would be one other alternative, right? So I could do ... could say that there's going to be another one. But wait, there's more. Who says I can only have one double bond? Take a look. Here's our structure with one double bond. Can you see the possibility to make 2 double bonds? I'll bet you can. What if we move that pair here? And so then the sulfur atom has 2 double bonded oxygens drawn thusly. Is it the same structure as the one on the left? No, this is different. This is new. That's another Lewis structure, but it has 2 double bonds instead of 1. So this would not be a resonance form of this. But this one would have resonance forms of itself because, in fact, yes, you can start to see it, I'll bet. We could put the double bonds opposing one another. And we would have at least how many more combinations? Would there be 4 more combinations based on that structure? So a total of 6? I think maybe that would be the case. So this is the concept. This is what we call resonance. There's a special molecule that's in our atmosphere that's very helpful for us. This is called ozone. There's no charge on that one. It's net neutral. 6 electrons per atom, so that's 18 electrons total. O goes in the middle. No other options, right? There's our pairs for bonding. Here's our lone pairs around the outside atoms for the octets, and there's a pair left over in the middle. That's a total of 18 electrons. Well, the central atom is not happy, is it? It's only got 6. So how do we fix that? Well, you guessed it. Either one side or the other, we're going to form a double bond, and we're going to see that oxygen now in the center is going to be happy because it's got a total of 8. So then one of the structures would look like this if we drew it with the line drawings. Can you see a resonance form for it? Sure you can. We have to have an equivalent structure that has a different arrangement of the double bonds. So what if we shifted that bond over to the other side? If we shift the bond over to the other side, that is a resonance form of the first structure we drew. So these 2 would be resonance forms of one another. Now, why does that matter? What difference does it make for ozone? Well, here's an interesting point. The interesting point is this, that actually acts as a shield for our atmosphere, okay? So if our ozone layer, and maybe you've heard of that before, is up there, this is not drawn to scale. Here's the sunlight. Something that penetrates towards the Earth is UV radiation, right? And that UV radiation has a certain frequency. And wouldn't you guess that these bonds have a frequency too? Those bonds have a certain frequency that's matched to the UV radiation. So what happens is those bonds absorb that radiation and it makes the molecule oscillate. Sometimes it splits, but the energy is sort of filtered out. The UV energy is filtered out, and what gets through is your visible light, your infrared light, and so forth. So it really does serve a purpose for us, right? So that's a little bit on resonance structures. I'm going to have a paper for you to work on today, and I hope this has been helpful.